All right, in this video, you see that we still are, well, in this video, we're going to calculate our accelerations. So I'm just going to go ahead and open up what we did in the previous video, and that's rotational motion 1-2-3, R for 1, 2, and 3. And once I do that, you'll see that we have all of our information here again. Still the same thing. Okay, and that's where we brought in our data sets. Okay, so now we want to look at the theory of what we're going to do. And so the first thing is let's calculate our acceleration. And so we can calculate our tangential acceleration, or we can calculate our acceleration. And what's interesting is like, well, how do you get your tangential acceleration? If we go back here, we'll notice that the tangential acceleration is just not tangential, but the angular acceleration is going to be the change in omega over t. Okay, and so we can find that for each one by, and I'm just going to follow this measurement right here. We have our angular acceleration. Basically, the acceleration should be, I don't know, shoes. Let's just test it and find out. So we can definitely find our radial acceleration. Our tangential acceleration is going to be based on our angular acceleration here. So we need to find our angular acceleration. And how do we find that? Well, it's just going to be the change in omega over time. Cool beans. So we should be able to find the initial position for omega and then some final for omega. But omega doesn't really change. All right. So we shouldn't have any acceleration. We may have a small bit, but if you notice that our angular velocity didn't change much. If we look at this, look at our angular velocity. Hopefully it connects properly. In other words, we didn't speed the rotation up. So since we didn't speed the rotation up, you'll notice that the angular velocity here is almost the same. It does change a wee bit, okay? It does change a wee bit from location to location, but if we take the initial point and we take the final point, that should come out to be 0 or very close to 0. So let's go ahead and I want to say let's do that, but let's just say that the angular acceleration is going to be 0 only because we see this phenomena in our data that it doesn't change much. All right, especially when we take the average. So let's find our, so what am I saying here? If that is 0, the angular acceleration is 0, that means that the tangential acceleration is 0. Okay? Does that make sense? In other words, our bicycle wheel isn't speeding up. That's what that says to me. But we do have a radial acceleration that we can calculate. So let's go ahead and calculate this radial acceleration, and let's calculate it for each one of these pages. So we're going to start off with page number 1, and we have our formula here. It's going to be the velocity, the tangential velocity over the radius. And so where's our tangential velocity? Well, here it is, right here. Okay, And there's another way to represent this. Let me see. I believe that our radial acceleration can also be written as this. Omega squared times r. So since we have our average for omega, let's just do omega squared times r to find our radial, or our centripetal acceleration, or our center-seeking acceleration. So we'll do that right here for each one. And so this is our centripetal acceleration. Okay, and we know that that is just going to be equal to, and let me make this a little bit bigger so we can see that, equals to the angular speed squared times the radius. So let's go back and find the radius. And I would really want this to be the average radius. So I'm going to go ahead and say that times average radius. And I'll just go over and collect all of these numbers here and drag down. Because the radius varies a wee bit. So since we didn't do this calculation, let's just do it in the, since we didn't do a calculation for the average radius, let's just do this calculation inside of this calculation. So it's going to hit return, and this is our centripetal acceleration. So let's see if that's going to change. I'm just going to say okay, and let's copy this. But before we copy it, let's give it color green, borders, and let's go ahead and copy, and let's go to rotational, our rotational page for number 2, and let's go to J, and let's paste. Okay. So that's our centripetal acceleration. And let's go here. And let's do the same thing here. Paste. So it's saying that as our R increases, the centripetal acceleration actually increases. So the force that acts on you is increasing. Okay? So a sharp bank, all right, you don't have as much, a lot won't keep you on the road. A greater bank will, you have more frictional force that can actually keep you on the road. That's what this is saying to me. Okay? And hopefully it's saying the same thing to you. If it's saying something different, awesome. Let me know.